which is the distribution that underlies the population or whatever we want to do, whatever the random variable we want to understand how it behaves. But we're not required to know that distribution. So this is, as we say, a distribution agnostic theorem. Is not known, or we don't need to know it. Then the central limit theorem is telling us that x bar, which is the sample average, what is x bar? It's this one. All those divided by n behaves approximately like a normal distribution with mean, the unknown mean, and standard deviation, that standard deviation, sigma divided by the square root of n. And that happens as the sample size increases, as n tends to plus infinity. So what does this behave approximately mean? Well, this means that we treat x bar as having normal distribution with these characteristics when n is big. What does big mean? Well, big means typically greater than or equal than 30, but if the distribution, if the data show that the underlying distribution is sort of symmetric, like the median is close to the mean, then that n can go even down to 15. Actually, for most of the cases, your book uses n greater than or equal than 15. I prefer n greater than or equal than 30.
And NP and NP minus 1 would be...
No, not for that, not for that. Oh. Not for that, that's for estimation of proportions. Okay? So this is what we have here. So let's see let's see how we can use this. This is a very simple case. So suppose that I have, and that's the strategy of use here. Suppose that we have a random variable x, any type of random variable, discrete or continuous, that doesn't matter. And we want to estimate. You never find, you estimate. An estimation means that there will be an error. We're destined to have an error. What do we want to estimate? The mean of x. That number. What we use when we want to estimate an unknown parameter, and unknown parameters for us will be the mean or the standard deviation. There are also other unknown parameters like the median, quartiles can be said to be unknown parameters, the kurtosis, the skewness. Those are things that come up in statistical study, metrics that depend on the so-called moments, higher moments, and all of those can be estimated. Now, of course, the higher the moment, the more data you need to estimate if you want to estimate correctly. That's the mathematical price that you pay, the mathematical cost. But here in this course, we estimate two parameters, the mean and the standard deviation. We care only about these parameters. And this is what we mostly do in 80%, 90% of statistical applications. Okay? So I focus now on the estimation of the mean. The strategy involves in building the so-called confidence intervals. And what is a confidence interval? We call them CI. A confidence interval is an interval which is kind of a small, basically B minus A is small. And the value of the unknown parameter belongs to this interval. The value of the unknown parameter we build confidence intervals. So this is a confidence intervals. The unknown parameter belongs in the confidence interval with what we say with a high probability, and that probability is called confidence. That's why we call them confidence intervals. Okay. Now, what I suggest is that you keep my notes as a guide, because this will help you to navigate inside the book, because those chapters are quite extended. They contain a lot of extraneous information, and I'm not going to cover all of this information. I'll try to keep it simple and practical. So when you go into the book and you use this as a guide, just highlight the boxes, highlight some boxes, or mark some material, the material that is relevant in the book, and leave out the extraneous information that is provided. The problem is that the book is kind of dense, and everything is the important versus the less important information is not marked at all. Everything is at one level. So the confidence interval will contain the value, and since B minus A is small, that's what I mean by estimation. The unknown value of the parameter will be between A and B, and the difference between A and B is not very big, so we get a fairly good idea of the value of the parameter, of the unknown parameter. And that happens with high confidence. High confidence means high probability. And I will use the central limit theorem now to build the first confidence interval, and this is the only confidence interval for which I'm going to use to show you explicitly why we construct it like that. But you will see me deriving it, and it's easy and fun. I'm not going to do it for the others. For the others, I'm just going to give you the formulas and give you the instructions under which we do this. Okay? So let's find the mean. We collect the data. Actually, when you collect the data, those give you some values. Those are our observations. These are trials, essentially, that we do. We try and measure, collect the data. That all this is basically, before you go and collect the data, you will collect N data. Each time you perform the collection of the data, you have a random variable. That random variable gives you one value, and exactly those are, as we call, realizations of the underlying random variable. And X bar will be nothing else after you have collected the data. It will be this. The values that you collected divided by the size of the sample. And instead of using X bar, sometimes we use this. Me with this hat, and that means point estimate. The hat means point estimate. So this means point estimate. And of whom? Of me. And it's a random variable. Or sometimes some people say, well, this is the value of the random variable. Okay, now this random variable is called estimator here. And I prefer always to go with a random variable and call that estimator or statistic. Some people call those statistics. And a statistic is a random variable which intended, after you perform the collection of the data, to give you a point estimate, a value, numerical value, which is close, it's intended to be close to the value of your unknown parameter. And now I will use that value of the point estimate to construct a confidence interval. You will see it will become more clear as we talk. Okay, we know that if n is big, the central limit theorem is telling me that I can use X bar as a normally distributed random variable. And this is the distribution. It is normal with this mean, the unknown mean, and this standard deviation. Now, the standard deviation involves a parameter that sigma may not be known. We have different avenues to dance around that problem, that we don't know sigma. Yes? Oh, he puts the variance. He puts the variance, sigma square over n. Am I correct? Yeah, that's an alternative way. I typically use, there are several schools for that. And I think pretty much schools are divided in the notation. Either they use for the parameters of the normal distribution the mean and the variance, or they use the mean and the standard deviation. I've been used to use the mean and the standard deviation. So you'll always see that square difference between me and the book. I write standard deviation, the book uses variance. Okay, so don't be bothered, adjust for that difference in notation. Well, thanks for bringing this up. So, although X bar does not precisely have a normal distribution, I pretend that it has a normal distribution. Why? Because n is big. And the theorem is saying that as n increases, as you collect more and more data, then the distribution of X bar more faithfully becomes normal distribution, becomes more close to being normal distribution. Okay? Therefore, what do I do now? X bar has normal distribution, so if I take z, which is equal to X bar minus me divided by the standard deviation, what is the distribution of z? Now, pretend that X bar has normal distribution because n is sufficiently big. I'm not making a big mistake for that. It has standard normal. Yes, so z has standard normal distribution because of this assumption. Well, let's write it. which holds approximately. So practically, Z has standard normal distribution. Now, let's say the following. Let's find an interval so that if the values of the standard normal distribution are between negative Z star and Z star, the probability, the values will be equal, let's say, to a desired confidence level, which is 95%. We can do this easily. We can look it up in the book. This function Z star can be taken. What should be the function of Z star? The function Z star. Actually, what Z star should be? Phi of Z star, what that should be equal to? Well, let's see what that would be equal to, how we will find it. Let's draw the picture here. So suppose this is the curve of the PDF of the standard normal distribution. You want negative Z star here and Z star here. Well, we have to see why is that. What I'm asking you is that the yellow area under the curve should be equal to 0.95. Correct? Because that area, the yellow area, represents the probability that Z, the random variable with a standard normal distribution, takes values between negative Z star and Z star, and I want this to be equal to 0.95. So I should draw Z star to the right, and its negative, its opposite, will be on the left, sufficiently far away from zero, so that this area that I have, the yellow area, is equal to 0.95. What is the area equal to what has been left out? The white area, as we call it, the tail area. In total, this area should be equal to 0.5, and since it is symmetric, it should be divided by 2. So this is 0.025, okay? So that phi of Z star should be equal to 0.025, and that actually allows us to find what is Z star. We'll look it up on the tables. What is the value for Z star? The appropriate value for Z star. Well, let's look up at the tables without disturbing the position of the table in my laptop, because we'll have a disaster again. Selected upper percentage points. Look at page 569. And you will see tail alpha. So what I'm asking here, this is the tail alpha. The tail alpha is equal to 0.025 if Z star is 1.96. So that from this we have that Z star is 0.196. Now we're in business. What is Z? Z is this fraction. So if x bar minus me divided by sigma by the square root of n is less than Z star, actually you can drop the star. Some people do have it, some others don't have it. Let's drop it and use 0.025 for this. Now I have an interval. And if I do the algebra, then you have me plus me minus Z 0.025, which is this 0.196, times sigma divided by the square root of n times x bar. Well, I want it. I want the interval. Okay, I want the interval. I want to have me. So let's multiply this inequality on all sides by -1. What you will see is that you have this inequality now. So from this inequality, what I have is that x bar minus the multiplier times sigma divided by the square root of n I have this. And this is a confidence interval which contains the value of the unknown parameter mi with probability 95%. Why 95%? Because if you reverse all of my computations, then you end up with this here. And since this has standard normal, I have already guaranteed by the selection of the point of the multiplier that this probability is valid. Yes, I went down. So the interval with these endpoints is called confidence interval, and it's actually the 95% confidence interval for me, actually, for the unknown mean. And that does not require for me to know the distribution of the unknown random variable. It's a distribution agnostic application, thanks to the central limit theorem. Now, of course, that involves that, because I used an approximation of a normal distribution, and we know that the quality of this approximation increases as the number of samples increases. As you see, the only thing that another thing that increases as well is the quality of the estimation, which is the length of the interval. What is the length of the interval that we estimate? The length of the interval is equal to 2 times the multiplier, which was found to be 1.96 times sigma divided by the square root of mu. So the more data I have, the tighter the confidence interval is. Therefore, I require a sufficient number of data, not only to have a tight confidence interval, but also to have the guarantees of the central limit theorem. N greater than or equal than 30 is a good number. You should know another thing. The more skewed the distribution is, the more data we need. What is a skewed distribution? Well, I can show you a skewed distribution. No, the X bar is what it is.
That's a big deal in one way or the other.
Skewed distribution is if it has a tail. For example, if the PDF comes like this, the Poisson looks like this. This is skewed to the right. Yes. Chi-square also is a good example of this. Now, the normal distribution is perfect because it's symmetric. A measure of the skewness is how close is the mean to the median, or how close the median is to the symmetry axis. So if you have that kind of offset, then you need more data, because the convergence of the standard deviation is bigger because you have the skewness of the data. So that slows down also the convergence of X bar, of the distribution of X bar to the normal distribution. The central limit theorem does not give you any indication about how fast this distribution is. It's only telling you that it's happening. as n tends to infinity. But it doesn't tell you the speed in which this convergence is happening. Therefore, you need to have some intuitive rules, and those are the intuitive rules here. We use n greater than or equal than 30, but if the data are quite symmetric, we don't have a lot of skewness to the left or to the right, then even n equal 15 can be sufficient. Okay? So, when we solve these problems, two are the things you need to refer. Things to observe. And you have to discuss. First, having a random sample. Second, either it's given by the problem or you assume that the sample that you have is random. That's what all statisticians do. Of course, there are procedures under which we try to have a random sample, but sometimes we can't. Second, or at least we do the best we can. You can't do more than the best you can. So you don't have to worry. Second thing is n is greater than or equal than 30 or 15 or any number in between 30 and 15 depending on how skewed the data are. I will show you a simple trick to understand whether the data are skewed or not. Third, and that's it, I guess. So this when you solve confidence interval problems. All right? Yes. Assume that it's random. But in some cases, I may ask you, if I give you conditions under which the sampling has been done, sampling meaning selecting the random variables x1, x2, x sub n, or the individuals which you are going to measure, the subjects you are going to measure. Then you probably have to argue why this leads to a random sample. I'm not going to do that often. I may do that sometimes when I give you a... actually, that has... I was kind of observing such a show. Actually, it was a 60-minute show. No, a 2020 show, or a nighttime. The Hansen Files, about pharmaceutical companies doing some tests in India. So let's summarize the discussion that we had so far. The quantity sigma divided by the square root of n that we had above is the estimated standard error, or sometimes it's called standard error of estimation. The number z that we calculate here in this example was 0.025. This is in general the z of a parameter alpha over 2. I haven't defined alpha yet, but just take that for granted for the time being. It's called multiplier. and depends on the level of confidence we want to have. This parameter alpha, that's a Greek letter. Statistics use quite a few Greek letters. Is called significance level. And the significance of the significance level is that 1 minus alpha is equal to the confidence, what we call confidence. In the previous example that I did, I calculated a 95% confidence, I constructed a 95% confidence interval. Therefore, my therefore the significance level was equal to 0.05, which gave alpha over 2 to be 0.025. Okay, that's the. So those are important parameters. Now that, as we mentioned here, this is the confidence interval, and let's go back a little bit to the properties that we need to have. We need, first of all, to have a random sampling. We talked about what a random sample is during the class. And also we mentioned that if, let's talk about n, the sample size a little bit, because that's significant. Sample size. If x, the random variable of whom you want to find its mean, you want to estimate its mean, has unknown distribution, or a distribution that is known but is not normal, then n has to be greater. It's better to be greater than or equal than 30, but even a smaller n can work if the distribution if it's PDF I don't want to put x is PDF, is not skewed. I would say it's not very skewed. Okay, so that's here that's the rule that we need to use. If x has normal distribution, then you have no restrictions for n. Because, as we have shown, x bar has normal distribution itself. So you don't really need to invoke the central limit theorem. No use of CLT is necessary in this case. Now, where else do we have the where else do we have the sample size being involved? Well, although these are the minimum requirements that we need for the sample size. In this case, we have none. In this case, we have n equal 30. That's my, or n equal 15, depending on how depending on whether the density of X is skewed or not. There are some more requirements sometimes for the sample size if you want to achieve a high degree of accuracy in the estimation of n, in the estimation of the mean. And let's see what would determine that high degree of accuracy. If you want a high degree of accuracy, what is your interval that you use? The length of the interval is actually determined by this quantity here, because that's the radius of the interval. So you want to be close to this quantity, close to the true mean. The true mean can be anywhere between these numbers. So how close the true mean is between any of these numbers depends precisely on the length of this interval. So the accuracy of the estimation of mean the estimation of mean will be, the estimate that we give for me is the number x bar. So the difference, the accuracy of the estimation is the difference of x bar minus mean in absolute value, which is of course less than or equal than the radius of the estimation you want, of the interval that you have created, of the confidence interval. Therefore, you want x bar minus me to be less, it's already less than the multiplier times the error of estimation, the standard error of estimation. And if this you want to be less than a certain number, let's call this certain number E, that will prescribe, that inequality here, actually that inequality here prescribes a certain value for n. Now, what you don't know here is the sigma. So if you don't know sigma, estimate or make a guess, make a sufficiently big guess for sigma. Based on the mechanics of the problem or based on what you're trying to measure. For example, if I'm trying to measure the height of people, I can make an estimation for sigma to be 1 foot, plus minus 1 foot. So that's something that may sound very big, but it's only being used to determine the sample size, not used to determine the statistics. So with that guess of sigma, we solve this inequality. E is your desired accuracy. So from this inequality, we know the quantities E, that's what we determine. That's a priori determined, the desired accuracy, we set that. We have a guess for that. This comes from the tables. So we solve this inequality with respect to n, with n being the unknown. And that inequality gives us that all d squared, sigma squared divided by n. And the thing that we do is that, we select an integer number which is greater. So the answer is to select an integer number greater than this quantity on the left-hand side. And that is basically the floor for the sample size that we require in order to have the desired accuracy. Of course, that might be a bigger sample size, and as I said, it's a bigger sample size if it depends on a crude estimation or a bad estimation or a very generous estimation of sigma. Now, sometimes sigma is known from prior studies or from previous surveys, and therefore sometimes this helps us to make that sample size smaller. But typically studies have n's that are much higher than what they actually need, especially studies that that are involved in engineering. On the other hand, if you do medical studies, sometimes you are forced to work with small sample sizes, and that creates certain limitations. If you don't want to have any limitation for the sample size beyond what is reasonable, then of course you need to be able to assume that X has a normal distribution. And we'll come back to this later, because when X has a normal distribution, X bar has a normal distribution, and therefore we have no restrictions for the sample size. We don't have that restriction any greater than or equal than 30. But if the only restriction that comes is from the accuracy. So let's summarize this discussion here. Sample size determination. If X has a known distribution or does not have normal distribution, then select n to be greater than 30 or this accuracy. If X has normal distribution, select n to be greater than I think I need to add something for desired accuracy E. Okay, so if we want to get the highlights of what we have done so far, I would actually put them in some boxes. This is our confidence interval. We need a random sample. These are some basic determinations for the sample size. And if we want to achieve a certain level of accuracy for the sample size, then we have to use this. Now let's move to a different subject, a different problem, which arises often in biology studies or in medical studies where the number of samples that we have is not known, is not sufficiently big, because we cannot collect many data. There are physical problems physical limitations that do not allow the collection of a sufficient number of data points. So in this case, what we have is that we work with small samples. That's the problem that we want to talk about. And this problem arises from the fact that when we use the confidence interval to estimate the mean here, this quantity is not known. So since it is not known, how can we find the interval? We have to replace it with something that we know. And what we know, the quantity that we can calculate, is the so-called sample standard deviation, which is given in the form of the sample variance, and the square root of the sample variance is the sample standard deviation. So this quantity is 1 over n minus 1 sigma x bar minus x bar squared when you add from 1 through n. Now, if n is greater than or equal than 30, even if the distribution of x is not known, replace sigma with s, which is the square root of the variance here, the sample variance. You can do that easily. So this is how we deal with cases where we don't know the sigma. Now, if sigma is unknown, and believe me, it's never known, and n is less than 30, you are forced to work with a small sample, then you must work in a different way. And this is called small sample estimation. That's what I want to describe next. In this case, x must have normal distribution. You must be able to approximate that, or you must be able to say that, well, x has is very close to having normal distribution. Any significant departure from normality will cause problems. Then the estimation of the mean is being done in the following way. The unknown mean is between x minus, we use here a different multiplier. Here this is n minus 1. Let me make it a little bit bigger because you will be having a 800 by 600 resolution, and that might be, so this is n minus 1 here, times s divided by the square root of n. And where does this multiplier come? This multiplier is, it's actually the quartile it's not the quartile, it's the quantile. It's the 2.5 highest quantile, where F is the CDF of the T distribution or student's distribution with, as we say, n minus 1 degrees of freedom. And since degrees of freedom is a very long phrase, we just abbreviate it with df. What is student's distribution? Student's distribution was discovered precisely from this problem by William Corset, who wanted to estimate, he was doing a quality control for the biggest beer producer in Ireland at the beginning of the 20th century. So he wanted to see if they don't cheat their customers, and they put the appropriate amount of beer inside the bottles, and therefore he looked at the problem of estimating if the entire production works well, if the mean quantity, by estimating the mean quantity of beer that is being placed in its bottle. That mean quantity should have been equal to the nominal quantity that the bottle is supposed to contain. It's written on the label, so many ounces. And he invented this distribution, but he did not publish it in a paper because he wasn't allowed per his contract, and therefore he published it by using the name student in some mathematical journals, and ever since that distribution got his name. So what is the important thing with this? The important thing with this is that when we know that x has a normal distribution, then actually we do not need to use the previous type of estimation. We can directly use that one. So if x has normal distribution, use the confidence interval we will solve some problems, so I will show you how we find those multipliers. To estimate me regardless of sample size n. I don't care, your book actually articulates on page 234 about the derivation of this. I don't really need, I'm not asking you to know that thing. Just leave the derivation out. Just focus only on this particular fact and learn how to use it by looking at the examples that I will prepare and present. And I will also work here in this lecture. Now, I would say let's work on some examples here. I will not tell you exactly where the example comes from. I will just tell the story. And after we work the example, then I will tell you which chapter or which section this came from. Some coffee. All examples come from chapter 4. Let's see, the breaking strength. We try to test the breaking strength of steel beams. So we bend the beam and we try to see what's the weight that if you put in the middle will force the beam to break. So you exert a force here, force F. And if that force is very big, then the steel beam will break. That's how also the Titanic broke apart when it was sinking down, and you will see that extensively next week, I guess. We'll all see that. Because the water and the weights were so, the water in the front and the weight of the engine in the aft of the ship were so unequally distributed that were exerting a force that broke the steel bars of her keel. So if that's a random variable that I want to estimate, because why is it a random variable? Because all of those beams may have some small variations, very light variations in the quality of the construction. So that F is not always the same. So that's a random variable. So breaking strength. We want to estimate the expected value of F, which is this me here. So we take a sample of N 32 beams, all from the same construction, and we test them independently of one another. So this independent testing, guarantees that we have a sample, a random sample. So we're done with this property, the random sample, and we also have a sufficiently big sample size, greater than 30, so we don't really need to articulate about the distribution of F. Now, if you had a smaller sample, or even if with this sample, you can always articulate and say, well, or you can argue, I believe that the distribution of the breaking strength is normal. Now, if you don't, I will tell you how you can do this, or whether you can do this. Typically, somebody who does a proper statistical study would plot the points, will do the QQ plot or the normal plot. Just take the data, the 32 data points, take the 32 data points. Those things can be done so easily these days with all the statistical software that is available to us, and make a normal plot. And actually this statistical software that will do that, the normal plot, as you recall, is the quantile to quantile plot, or QQ plot. When you use the data points, when you plot the CDF of your sampling distribution against the CDF of the normal distribution, of the standard normal distribution, actually. And if those points are in the diagonal of this square that you plot, then, or very close to the diagonal, then we say that they come from a normal distribution. If they start departing from the diagonal, then they don't come from a normal distribution. And in this case, if they come from a normal distribution, actually the statistical software is giving you that. The point estimate for me is giving you everything that you need, even the confidence level. Now, suppose that you don't have the ability to do the QQ plot. You can do something which is much easier. Do a box plot. Take your data and plot it. So if you do your box plot, you will have Q3 here, Q1 here, minimum, maximum, and somewhere here is your Q2, which is the median. Now, if the data come from a normal distribution, then that quantile here, the second quantile, the second quartile, should be equal to the mean, or very close to the mean. So these two distances must be equal, or approximately equal. In this picture, I would say, yeah, the data are come from a normal distribution. If the distribution is not terribly normal, it's approximately normal, then it's still okay, because you have a quite good sample size. To summarize this discussion, here actually with the sample size of 32, I didn't really need to bother about that because the sample size is sufficiently big. For a smaller sample size, I should have done this type of analysis. So the data tell me that X bar is equal to 13.2. No, sorry, excuse me. No, it has to be bigger. It's a still bar. I'm reading a different problem. 42,196 pounds per square inch. And the problem is telling us that from the past experience, we know that sigma can be taken equal to 500 pounds per square inch. Actually, this is PSI. That's the unit, pound per square inch. Let's find the interval. Let's find the 90% confidence interval. For me. Well, we have to look at the numbers. The 90% confidence interval would be actually this X bar minus Z. I have a big data set, so I can use 32 here and use the Z. What is alpha over 2? Here my alpha is 0.05, no, 0.1. The level of significance is equal to 0.1. So alpha over 2 that I need here would be 0.05 times the known sigma that has been used, divided by the square root of 32. So that will be actually the known sigma will be the 500. X bar is the value that we have here, 42,196 pounds per square inch. What is, if we look at the tables, this Z of 0.05 would be equal to 1.645. And therefore, if you do all the math, that's what you have. And that actually solves this problem. That's the solution is complete now. So this is the 90% confidence interval for the mean, which means that where with probability 90%, the true value of the mean of the average breaking strength of the examined steel bars will be between these values, and sometimes you read this sometimes you will see that instead of mean, you're being given that's the most typical way to report results. You will be given the point estimate of this parameter, which is 42,196. That's the sample average here. And the error of estimation will be 1.645 times a plus minus error. That's a different way to report the results. Or you can report this quantity as a percentage of this quantity. That's another way to express that. In the problems, I'm interested to see this, and here's where your solution stops, and you need to add a sentence, and you can say that therefore the expected or the average breaking strength of the examined steel bars is it satisfies the following inequality. That's the way you can phrase it. Now, in this problem, I use the Z distribution to do my calculations because it's easier. I have 32 data points. Now, one could have argued that I could have used the T distribution by making the assumption that the sample is actually F is normally distributed, which is another reasonable assumption, to assume that F is normally distributed. In many of the problems that we use, we don't care whether the assumption about a random variable having a normal distribution is true. We care about whether it is believable or reasonable to be true. So that was example 422. Let me add something else, and So we can move a little bit ahead. Suppose that we have two random variables. We want to estimate the mean of their difference, and of course we know that this is the difference of the means. So that's a problem of estimation of these two. Now, to do this estimation, we must have that x and y are independent random variables. Without this, we cannot proceed. So that's actually, I'll put it in the red box. Here is the recipe for this estimation. If x and y do not both have normal distribution, we need the sample size from x and the sample size from y. Those do not have to be equal, both to be greater than 30. Okay, so that's the requirement for the sample. So we need fairly big sample sizes when you estimate the difference in the mean. Then the interval that we use for this estimation is I will continue. Okay, and if an x and an y are both greater than 30 and sigma x or sigma y are not available, replace them with the sample variances, the sample standard deviations. So this is how we estimate the mean of the difference of two means when we're distribution agnostic and we have big sample sizes. So now the last two things we want to talk about is the first is the so-called tolerance intervals. That is in a very messy way explained in your book in section 431. However, I would suggest to not touch that section at all. Just read what I'm going to present here and stay with my material. Because the book is a bit confusing and I also leaves gaps. Now, a big problem is the following. So far we have estimated X bar. We have estimated the mean of a random variable. And the random variable has a distribution. Now we know how to estimate when this distribution is normal. We know how to estimate when this distribution is not normal. But the mean by itself will not tell us very many things. For example, suppose that we have an estimate for the mean. And that, let's go back to the experiment, to the problem we solved before with the metal bars, actually the steel bars, under braking force. So the fact that the average braking force is what it is not going to tell us what is the upper limit of the braking force of this bar, or what is the lower limit of the braking force of this bar. And when we see, so when we ask find upper and lower bounds for the braking force, we ask for a tolerance interval. So if F is the braking force, what is the lower bound L and what is the upper bound U that we need? That actually we know that with a high degree of certainty, if the F ranges between these two values, the bar will break. Think of it in another way. Suppose that a factory produces washers or screws, and those screws must have a certain diameter, must have certain specifications. All the screws have minute differences, variations from those specifications. Therefore, what you're interested to know is what is the lower bound and the upper bound within each of the specifications is with a high degree of certainty. Now, this is different than confidence interval estimation, but depends on confidence interval estimation, and it's called tolerance interval. So let's go back to F, although you don't really need to know about a lower bound, but you need to know about you need to know about a lower bound, because once you exceed the lower bound, then you may have a breakup with a high degree of certainty. So essentially, if you want to say, well, this steel bar can sustain weight in its middle that can be so big, well, you're interested to put this number L as the specification, because you know that if you go above L, it's quite likely that the bar is going to break. How do we find this? So the problem is that I want to find those lower bounds and the upper bound, so that if F is within this, the breakup will occur with a certain degree of certainty. And again, I'm using my alpha, my significance level here. So this is a tolerance level. And schematically, what we're talking about is the following. If the mean value of F, let's put F bar here. Suppose that this is the confidence interval, F bar minus what we have, F bar plus what we have here. Let's call it, we call it E. That error, and that E was what we used before in our example. So the mean of F will be somewhere here. But you know that if the mean, for example, is here, if the true value of the mean is here, the red, that's the mean, that's the expected value of X. Then the values of X will disperse around this mean. But as you depart from this true value, it's less likely that you will find values for this breaking force F. So we want to find a bigger interval, perhaps this interval, within which we know that if F lies within this interval, then the bar will break. And of course, since you're talking about the breaking part, a breaking force, you're interested for the lower bound. So that's the lower bound here, that what is of interest to us. There are two ways to do this. There's a I would say a distribution agnostic, which is not a very good approximation. And there's also a slightly more accurate, a quite more accurate way to solve this problem if we assume, and this is what I will do to find a tolerance interval. We assume, or we must be able to assume, that the random variable F has normal distribution. So that's very important. Beyond the case of normal distribution, then the only other way is to use a sort of a weak form of inequality, a weak form of solving this problem via Chebyshev's inequality. But nothing will be sufficiently accurate. So we need to give even bigger tolerance level, and sometimes that's not very, very practical. So we assume that x or our random variable has normal distribution in order to solve this problem. Then the tolerance interval cannot very easily I can't show you precisely the procedure in which you will use to approximate it. The lower bound will be this x bar or f bar, whatever you want, minus k. K is a number, is a factor, that's a multiplier, and I will tell you how to find this multiplier. We will use some tables, times the sample standard deviation. The upper bound is x bar plus the multiplier times the standard deviation. That's actually lowercase s. And you remember what that s is. We mentioned it already in formula above. I'll just try to get this formula here again. That is the formula which we use to evaluate s. And everything now depends on the data. So the probability that this will happen is 1 minus a, and to find k, from tables. Actually allow me to make a certain change here. Suppose that you pick a value between p and a. You find you will find this from. So the problem is that I want to, if I preset the value p, I want to be able to find k. X bar and s are found from the data. I want to be able to find the value of k, so that multiplier secures that I have the lower bound and the upper bound of the population or of the values of the random variable to be inside this interval, which is called tolerance interval with probability p. That also depends on another parameter. The other parameter that we need is a, the significance level, which we use to find x bar, and with which we have the estimation, which we use for the estimation of the mean. In this calculation, in the output actually of this calculation, you don't see where the what actually p, what actually a is. You essentially are interested in the following problem. You're interested in the following problem that essentially the values of x will be in the interval with probability p. So now, if we go to table, it's table C9, page 575. You see the following values for the tolerance limits. Suppose that we start with confidence 0.95 and which means significance 0.05. We have a sample, let's say, of 32. I'm referring again to the bars. 32 is the number of the steel bars that we have tested. And you will see that you won't find 32 precisely in the interval. If you don't find the value, just use the closest value which is reported. So I will use n equal 30 because the line for n equal 32 does not exist in this table. If I want to be 90% confident, then what I use is that I pick my my sample variance. Suppose that I had my sample variance. In the previous example, we didn't have the sample variance. So, but we had, I think, 46 something, 42.196. You remember that the confidence interval had a multiplier which was 1.6 1.645. I think so. Here, the confidence, the multiplier goes up to 2.14 times. I can use the sigma instead of S because somebody gave me the sigma. S is an estimation of the sigma, but if you have the sigma, you're fine. So this is a tolerance interval for F. In other words, when F exceeds this value, 192 I think it was, the steel bar will break with probability 90%. But this is exactly the definition, this is exactly the use of the so-called tolerance limits. And if you want to report that do not exert a bigger pressure on the bar, and of course you will not bring the bar up to its maximum almost limit, which is 90% confident that it's going to break, you will probably want to lower this a bit. You would say, well, I'm using a bigger number here. I'm using a bigger multiplier. And exactly, there are formulas which actually give you this, but it's beyond the scope of the course to produce that formula here and to talk about this formula. Now, to close this section, or this part of the section, we're not done with section 4.3. We'll continue with section 4.3 in the next lecture online, which will be posted sometime tomorrow, Saturday, April 7th. I would like to solve a problem I'm actually going to pick it up from section 4.2. And I'll do problem 4.2.4. So the problem says the following. Suppose that I have the average biological oxygen demand at a particular station has to be estimated. For measurements at other stations, we know that the variance is about 8, the variance of BOD is about 8.0 milligrams per liter, per cubic liter. Well, that's actually milligrams per cubic, all of it square. So that's the variance. So if X, let me read the problem and then we'll go to X. The average biological oxygen demand at a particular station has to be estimated. From measurements, we know that the variance of BOD measurements is about 8.0 milligrams per liter square. So that unit here comes because we have the variance, so the variance is the square of the standard deviation. So the standard deviation of BOD is the square root of 8 milligrams per liter. How many observations should we sample if we want a 90% confident, to be 90% confident that our sample average is within 1 milligram per liter of the true mean? So here, as in all problems of estimation, we begin with identifying the random variable of whom the mean we want to estimate. So that's the first step. If you don't know the random variable, then you will have trouble following the problem. Okay, here what we want is the biological oxygen demand. So then X is BOD in milligrams per liter. Now, what can we assume about this? Well, we are not being said anything about the about this X being normally distributed, but we can assume that X is normally distributed, or since we do have the variance, somebody gave us the variance, we don't really need to know anything about the distribution of X. You see how I build my case? I go through the checklist for each problem. I go through the checklist of what I have to find in order to solve every problem. And here I'm doing a problem of estimation of the sample size. If X had the normal distribution, then I could be using that estimation from using the t distribution if I don't know the variance, or another approach is to use the z distribution if we know the variance. Now, since I know the variance, but I have not made any specific assumptions about the distribution of X, we will assume that X is not very different from being normally distributed. So we can say has an approximate normal distribution. Or has a distribution which is not very skewed. doesn't matter that we have big variability. The skewness in the variability is the big problem. We take n to be greater than 15. How do we get this n greater than 15? We get this n greater than 15, that since because we will use the central limit theorem for the estimation of the mean. We have not assumed anything for the distribution of x, except that this distribution is not very skewed. Well, we believe this to be true because we have a biological or a chemical quantity. So sometimes often when you have chemical quantities, that assumption is very plausible, that this chemical quantity has approximately normal distribution. It's actually quite unlikely that you will see the opposite happening. And based on this assumption, we will use a sample of n which is greater than 15. So whatever we'll find, this is a problem of sample size identification. We will need to take the sample to be greater than 15 for this particular reason, because we have made no specific assumptions for n. Now we want to be 90% confident, so what is E? E is z of 0.1 over 2. We want confidence to be 90%. Therefore, alpha is 0.1. That gives us So we have z of 0.1 over 2, sigma, divided by the square root of n. And we want this epsilon, this E, the error, to be within 1 milligram per liter. So the z.05 sigma is known, is 8, square root of 8 actually. If we, and this is 1.645, therefore now 1.645 is going to be roughly something like at the order of 2.3. 1.645 squared should be greater than 2.3 times 8. That gives us more than 16. So the number we have, pick an integer number. Our sample size can be any number. You want this n to be greater than this number, and 15, because you have already assumed that x is approximately normally distributed, but not exactly normally distributed. You allowed some freedom there. Must be greater than this. So, for example, n greater than 20 satisfies all of those properties. So that's a sufficient answer for this particular problem. Let me solve a final problem of estimation. I'll do problem 2 in page 422. The mean and standard deviation of n equal 42 mathematics SAT test scores is x bar 600 equal to 680, and the sample standard deviation is 35. So basically the problem is giving you all you need. And this is SAT test scores from the entering freshman class of a large private university. Find an approximate 99% confidence interval for the population mean me. Well, forget approximate, find 99% confidence interval for the population mean me, and the book calls that approximate because the distribution of the random variable, which is x here, SAT score of a random freshman, of a freshman admitted at this college, by this college. Although SAT scores are integer numbers, I will consider them as continuous random variables. Otherwise, you have a very difficult random variable to model. And of course, that has an added value that we can consider x to be approximately normal or close to normal. Actually, do we need to make any assumptions about the distribution of x? We actually can do that because n is 42, so it's greater than 30, which means two things. No need to know the distribution. Of x to estimate the mean of x, because that's what we need to estimate. Estimate the mean of x, that's what the problem says. And also that says that we can replace sigma with the sample standard deviation, S. So the tolerance, the confidence interval, the 99% confidence interval will be the mean. We need 99% confidence, so alpha would be 0.01. So alpha divided by 2 will be 0.005 times S. So that's the confidence interval now. What is Z.005? If we look at the tables at the end of the book, this is 2.576. So we have the interval now to be 680 minus what is S equal 42 and S is 35. Is the 99% confidence interval for the average SAT score of a freshman admitted by this college. It's very important at every problem, when you finish the problem, to include this kind of simple statement which describes the quality of, which describes your result. Okay, what other people would have done? Probably other people would have reported 680 as being the average SAT score. However, this is not correct. The average SAT score is the mean of the random variable x, which is SAT score, and not the sample average. Sometimes people in practice are confused and report the sample average as the mean. However, and they produce that as an estimate. You can certainly do that, but if you do this, then you have to say, you have to express this quantity as a percentage of 680 and say with this error plus minus this error. And that's where you calculate the error from. So if you want to say the average SAT score of a freshman admitted by this college is 680 plus minus the following number. And that number will be expressed as a percentage. And I multiply by 100 because I want to express this, all this thing as a percentage. And that's exactly the error. Sometimes you see on channels or on broadcasting or report of statistical examples, statistical results. Well, I guess with this I will close here, and I wish you a nice weekend. Please watch this video and watch also another video that I will upload tomorrow.